Okay, so the other thing that becomes important in the atmospheric and oceanic circulation and in climate is the multiple scales of motions, dynamics, thermodynamics, and interactions between these multiple scales. And there are many instances where the energy goes from small scales to large scales, which is rather counterintuitive. So let's touch on a little bit about the description of small and large scale motions. So this is showing an illustration of eddy fluctuations. We haven't defined what an eddy is. We will see what that is in a minute. Air velocity u and another physical quantity c could be particle density or humidity. So could be aerosols, could be black carbon, which is also an aerosol, but nonetheless, bold lines designate the mean values of u bar and c bar. So those are the long-term averages. Could be a minute, could be a day, could be a week, depends. Tau is the averaging time. So here is the time axis, here is u, and here is some other quantity c. So you see that there is the long-term average and there are high frequency fluctuations within that. So we will see an example of the ocean circulation from that. In this case, basically we can divide the velocity u into the average over a long time u bar and then deviation from that u prime. By the way, this also can be done in space where you have spatial wavy features which are acting on a background spatial average. So you can also look at deviations from the spatial average, zonal or meridional, and this is the same here for C. How does it work? Let's look at this example from YouTube. I don't know if this will work. Oops. Hello. Okay. Let me get away from the laser pointer, and now it should work. It should take me to the YouTube channel here, and you can probably hear the sound as well. I'm not sure, but just as an illustration, you have features like the Gulf Stream, and the Gulf Stream is not a steady feature. It's constantly breaking into these eddies, and there are loop currents here in the Gulf of Mexico. There are rings, Brazil rings, and other rings coming off of here. So this is what the ocean and atmosphere look at when you look at it at some high spatial resolution. So you have mean currents riding on top are these features of a smaller scale, higher frequency that are called eddies in general, and there are many ways to think about these, but just to give you a sense that when you average over those, there is always a question of whether they are leaving any signature on the frequency or not. And obviously here we are saying this mean is not independent of those deviations from the long-term mean. Okay, so how do we go about describing those? Here we are looking at u. It can be written as u bar plus u prime, where u prime are the deviations from the mean. So u bar is basically the average or the averaging time from t1 to t2 of u, the total dt, where tau is of course t2 minus t1, and similarly c is c bar plus c prime, where c bar is 1 over tau t1 to t2 ct dt. Similarly, for our previous source equation, we can write p bar plus p prime, where p bar again is 1 over tau t1 to t2 pt dt, and the average of u prime has to go to 0. That's the definition of the u bar and u prime. So u prime averaged over the same time is 1 over tau t1 to t2 u prime dt, but by definition u prime is u minus u bar. So u bar is already the average independent of time, so that comes out, and the integral of u bar over t1 to t2 is u bar the integral of ut over t1 to t2 is u bar itself, so u bar minus u bar is 0. So time average of these eddies is 0. Then you can plug it into the equation. We looked at the advective diffusive equation, d dt of ct, where c is c bar plus c prime, and we had duc dx, so again you write u as u bar plus u prime, c bar plus c prime, and then the diffusion operator was d dx of d dx c, where c is again c bar plus c prime. Then we had the source sink term, which also can have an eddy component. Okay, so you can split that into dc bar dt, which has to go to 0 because c bar is constant, dc prime dt minus du bar c bar dx minus du prime c bar dx minus du bar c prime dx, and then d dx of u prime c prime. So here you have the similarly d dx of dc bar dx. Remember, this is the diffusivity, d dx of partial x of dc prime dx plus p bar and p prime. So this is the advection of the mean value of c bar by the mean flow. This is the advection of the mean quantity by the eddy currents. This is the advection of the eddy component of c prime with by u bar, mean current, and this is the advection of eddy component of c prime by the eddy component of velocity, and similarly here. So those are kind of terms that become very important based on various situations of which time scale you are looking at. So you can look at daily time scale with respect to let's say intra-seasonal time scale, or intra-seasonal time scale with respect to seasonal time scale, interannual time scale, and so on and so forth. So take the average of this equation. dc bar dt average is basically d dt of c bar, which is obvious, and average of this will just give you du bar c bar dx. Average of this will give you d dx of dc bar dx, of course, because c bar are already averaged over time. These are time averages. The time average of p bar is again just p bar, and by the same token as we did before, the time average of dc prime dt is 0. The time average of du prime c bar dx is equal to du bar c prime dx. Both of them have to go to 0. When you take this inside, it becomes time average of u prime, which goes to 0, time average of c prime, which goes to 0. Similarly, time average of c bar c prime goes to 0, time average of p prime goes to 0. So you end up with this equation. Did I say this was 0? I was wrong about that. So change in the mean quantity over time, that need not be 0. Depends on how long you are integrating. So dc bar dt is minus d dx of u bar c bar minus d dx of u prime c prime bar. So it's the average of the product, not individuals, plus d dx of dc bar dx plus p bar. And here the average of u prime c prime is again, of course, u minus u bar times c minus c bar. So the flux here is u prime c prime time averaged, which need not go to 0. This is known as the eddy. It's the covariance between u prime and c prime. If they're completely uncorrelated, that would be 0, but typically they are not completely uncorrelated, as we will see. So there is always an eddy flux. So eddy flux of c prime by the zonal velocity is what we are talking about. What is done with it? It is considered like a eddy diffusion. So eddies are these high frequency oscillations, and they are not averaging out to 0. So they are moving material, energy, heat, temperature, momentum, whatever. So in this case, some c prime is being moved. So u prime c prime averaged over time can be written as some eddy diffusion coefficient times the mean gradient in the x direction. So gradient of the mean quantity in the x direction. So this is obviously a so-called parameterization. We don't always measure these things, but the net effect is that the mean is being affected by the diffusive effect of the eddies, which is represented here. So in that case, in the three-dimensional framework, this just eddy flux becomes vector u prime times c prime time average is minus k, similar to the diffusivity that we had before for molecular diffusion, times gradient of time mean c bar. So dc bar dt then is minus du bar c bar dx plus d dx of k dc bar dx, plus now we have the original diffusivity term plus p bar. It turns out that in the general atmospheric oceanic circulation on large scales, molecular diffusivity is much smaller than eddy diffusivity terms. So these large scale time fluctuations of flow features that we saw in the ocean animation, for example, they are doing most of the diffusion, and molecular scales are just too small to add to the large scale circulations, distributions, patterns of observed coupled patterns, coupled ocean atmosphere patterns. Okay, so examples of eddy flux densities: rho denotes a mass density, and rho s the particle or the mass density of salt, is just to keep parallel to the previous advection and diffusion terms. So for mass we have three-dimensional flux is vector u prime times rho prime average, so that is the fluctuation of density around the mean, which can be written as minus eddy diffusivity times gradient of rho bar, which is basically parallel to the molecular diffusion term we had written. Similarly, for heat, we are talking about eddy diffusivity of heat, which becomes minus k rho c grad t bar, and for salt, similarly minus k grad rho bar s, and the y momentum is minus rho k grad u bar y, where u bar y is the current in winds or ocean currents in the meridional direction. So this is our net equation then. dc bar dt is minus gradient of u bar c bar plus, so remember this is three-dimensional vector, and divergence of diffusivity, eddy diffusivity times gradient of c bar plus divergence of the molecular diffusivity we had done before plus p bar, the average source sink term. Okay, so we'll come back to explain more of this, but now this description includes the small scales and large scale motions. The question is always how the small scale motions add to the mean of the large scale, the so-called low frequency rectification. Exactly, I'm using the term rather loosely, but you know what it means. So here you can see that this one as drawn here has a slight increase, but let's not get into that right now. This is showing a slight decrease and so on and so forth. So we'll come back to this and look again in further details when we do actual climate examples. Okay, so for now let me leave this here.